Picture a night sky, but not the one you know, one where stars don't just twinkle alone. Instead, they dance in groups of 6, tangled in a cosmic ballet so rare, most astronomers go their entire careers without glimpsing one. These are sextuple star systems, stellar families where 6 suns orbit each other in an intricate gravitational embrace. And what happens inside these systems? Well, it defies almost everything we thought we knew about how stars behave. Imagine 6 stars, some so close they share atmospheres, others flinging planets into chaos, all bound by forces so complex they rewrite the rules of physics right before our eyes. This isn't science fiction, it's real, and it's happening right now in the darkest corners of our galaxy. For centuries, we've looked up and seen stars as solitary beacons, or at most pairs binary systems we could just barely wrap our minds around. But sextuple systems, they're the universe showing off. Less than a dozen have ever been confirmed, and each one is a Pandora's box of cosmic oddities. Some have stars so young they shouldn't exist alongside their ancient siblings. Others harbor planets caught in never-ending celestial tug-of-wars, where a single sunrise might involve multiple stars blazing across the sky. And then there are the mysteries, like how these systems even form without tearing themselves apart. It's as if the universe took our textbooks, scribbled question marks in the margins, and dared us to figure it out. That's where this journey begins. Over the next few minutes, we're peeling back the layers of these stellar enigmas, uncovering 30 discoveries so strange they'll make you question everything you thought you knew about space. From gravitational paradoxes to rogue planets with 6 shadows, these systems aren't just astronomical curiosities. They're keys to understanding the most violent, beautiful, and unpredictable forces shaping our cosmos. So buckle up, we're diving into the chaos, the beauty, and the sheer improbability of sextuple star systems. And trust me, what we find will leave you staring at the night sky a little differently tomorrow. The first time astronomers spotted TYC 7037-89-1, they thought their instruments were playing tricks on them. Hidden in the constellation Eridanus, nearly 2,000 light-years from Earth, this cosmic oddball turned out to be the first confirmed sextuple star system, a place where 6 stars exist in such perfect harmony. It's like watching a precision clockwork of fire and gravity. What makes this system so bizarre isn't just the number of stars, but how they're arranged: 3 pairs of binary stars, each duo locked in their own tight dance, all while orbiting a shared center of mass like a celestial carousel. The innermost binary pair whirl around each other in a dizzying 1.6 Earth days, so close their surfaces almost touch. The second duo completes its orbit in just 8 days, while the third pair, slightly farther out, takes a more leisurely 138 days. But here's the real kicker: all 3 pairs are gravitationally bound to one another, tracing intricate loops that defy conventional models of star formation. Astronomers stumbled upon this system while combing through data from NASS, a transiting exoplanet survey satellite, or TESS, which normally hunts for planets. Instead, it revealed a stellar Russian nesting doll, with each layer revealing new surprises. One of the most baffling aspects: the stars in TYC 7037-89-1 aren't just random siblings, they're practically twins. Each binary pair consists of nearly identical stars in mass and temperature, burning at around 7,000 degrees Celsius. This level of symmetry suggests they formed together from the same swirling cloud of gas, yet somehow avoided collapsing into a single, chaotic mess. It's like throwing 6 marbles into a spinning funnel and watching them settle into perfect pairs. A feat so improbable, it challenges our very understanding of stellar nurseries. And then there's the light show. On a hypothetical planet inside this system, the sky would be a kaleidoscope of multiple suns, casting overlapping shadows and creating sunsets where day and night blur into a perpetual twilight. Tidal forces would stretch and squeeze any orbiting world mercilessly, making survival nearly impossible. Yet the mere existence of this sextuple system proves the universe enjoys bending the rules. For astronomers, TYC 7037-89-1 isn't just a curiosity. It's a cosmic laboratory offering clues about how stars evolve in extreme environments and whether such complex systems could harbor planets against all odds. Gravity usually plays by ruthless rules. Crowd too many stars into one place, and you'd expect a catastrophic collision or a violent ejection. Yet sextuple systems like R Cassiopeia laugh in the face of that logic. Here, 6 stars whirl around each other in a space smaller than Neptune's orbit, locked in a gravitational waltz so precise, it's like watching 6 fireballs navigate a cosmic minefield without a single misstep. The secret lies in their orbits, which resemble a meticulously choreographed dance where every star knows its steps. Take the innermost trio, 2 tight binary pairs pirouetting around each other, while a third pair loops around them at a safer distance. Their orbits form a hierarchical structure. Think of a set of nesting dolls, where each layer operates independently yet remains bound to the whole. The closest stars complete their orbits in mere days, their gravitational pull balanced by the outward fling of centrifugal force. Meanwhile, the outer pairs move slower, their wider paths acting like shock absorbers to prevent chaos. It's this delicate balance between speed, distance, and mass that keeps the system stable over millennia. But stability doesn't mean tranquility. Simulations reveal these stars constantly tug at one another, their gravity creating ripples that subtly shift orbits over time. In most systems, such disturbances would lead to disaster, but sextuples have a built-in safety net: resonance. Like gears in a clock, their orbital periods sync up in ratios that cancel out destabilizing tugs. For example, one pair might orbit exactly 3 times for every 2 rotations of another pair, creating a rhythm that prevents catastrophic close encounters. The real marvel: these systems shouldn't exist at all. When stars form from collapsing gas clouds, the process is messy, like trying to bake 6 soufflés in one oven without any collapsing. Yet sextuples defy the odds, suggesting their birth clouds were unusually calm, or that some stars were captured later, like celestial strays adopted into a pre-existing family. Either way, their survival hints at gaps in our understanding of how gravity orchestrates stellar nurseries. And then there's the heat. With 6 stars crammed so close, their combined radiation bathes the system in relentless stellar winds. Any hypothetical planet here would face a barrage of ultraviolet light and gravitational kneading strong enough to strip atmospheres or crack crusts. Yet paradoxically, these extreme conditions might also create habitable niches, shaded pockets where multiple stars' gravitational pushes and pulls could stabilize a planet's orbit, offering fleeting safe zones in an otherwise inhospitable circus of fire. For astronomers, these overcrowded dances aren't just curiosities, they're stress tests for the laws of physics. Every sextuple system discovered forces us to rewrite models of star formation, proving that when it comes to gravity's creativity, we've only scratched the surface. Hidden within the tangled choreography of sextuple star systems lies one of astronomy's most precise tools: an eclipsing binary pair. These celestial twins orbit each other in such a way that from our vantage point, they periodically cross paths, one star dipping in front of the other like clockwork. It's a cosmic eclipse on repeat, and when this happens inside a sextuple system, scientists strike gold. The precision of these eclipses acts like a natural laboratory, revealing secrets about the stars' sizes, masses, and even their atmospheres with unmatched accuracy. Take the system V904 Scorpii, where 2 stars in a tight binary embrace eclipse each other every 2.4 days. Each time the brighter star slips behind its partner, the system's combined light dims by nearly 20%, a telltale dip detectable even across thousands of light years. But here's where it gets extraordinary, because this binary is part of a sextuple system. The gravitational tugs from its 4 neighboring stars subtly warp the timing of these eclipses. Those minuscule deviations, they're clues. By measuring how the eclipses speed up or slow down, astronomers can map the invisible gravitational fingerprints of the other stars in the system, like detectives reconstructing a crime scene from faint disturbances. The data is astonishingly precise. For instance, the eclipses revealed that one star in the binary is a puffy giant, its outer layers bloated by intense radiation from its companions, while the other is a compact, fast-spinning dwarf. Without these eclipses, determining their exact sizes would be guesswork, but because we see them cross directly, we can calculate their diameters down to a few dozen kilometers, an accuracy akin to measuring the width of a coin on the moon from Earth. But the real magic happens when stellar atmospheres collide. As one star passes in front of the other, its light filters through the outer gases of its partner, allowing spectrographs to dissect the chemical makeup of those layers. In V904 Scorpii, this revealed traces of helium being stripped away by stellar winds, a process usually hidden from view. It's like watching a star slowly unravel in real time, something only possible because the eclipses provide a clean, backlit view. And then there's the dance of shadows. In a sextuple system, the eclipsing binary isn't just interacting with itself. It's being watched. The other star's gravity tugs on the binary's orbit, causing the eclipses to arrive a few seconds early or late over months. These timing variations are tiny but packed with information. They've exposed hidden stars in the system, hinted at undiscovered planets, and even suggested that some sextuples might be temporary stellar families on the brink of gravitational divorce. For astronomers, these eclipsing binaries are more than just cosmic curiosities. They're precision instruments crafted by nature. Every dip in light, every wobble in timing, is a piece of a puzzle that challenges our models of how stars form, evolve, and interact in crowded environments. And as we find more of these rare gems nestled inside sextuple systems, one thing becomes clear. The universe doesn't just defy our expectations, it hands us the tools to rewrite them. Buried in the scorching embrace of the Carina Nebula, astronomers recently stumbled upon a cosmic toddler, a sextuple star system so young, its stars are still swaddled in the gauzy remnants of their birth clouds. Dubbed NGC 33245, this system is a mere 500,000 years old, making it the youngest sextuple ever discovered. To put that in perspective, when early humans were just beginning to walk upright, these stars were still condensing from primordial gas. Their infancy offers a rare window into how such intricate stellar families assemble in the universe's most chaotic nurseries. What makes NGC 33245 so extraordinary isn't just its age, but its environment. It's nestled in a region where star formation is frenetic, a place where gravity's tug of war with radiation and magnetic fields creates a pressure cooker for stellar birth. Normally, such dense environments spawn single stars or simple binaries, but here, 6 stars emerged in lockstep. Observations from the Atacama Large Millimeter Array revealed a tangle of dust filaments weaving through the system like cosmic umbilical cords, each channeling gas onto the growing stars at breakneck speeds. The stars themselves are mismatched siblings. 2 are colossal, already burning hydrogen at their cores, while the others are still contracting, their cores not yet hot enough to ignite nuclear fusion. This disparity suggests they formed in waves, some stars triggering the birth of others through shockwaves rippling through the nebula. It's a process akin to a chain reaction, where one star's formation squeezes nearby gas pockets until they collapse into new stars. In most cases, these later arrivals would be ejected or consumed, but in NGC 33245, they've somehow found equilibrium, orbiting each other in a precarious gravitational truce. The system's youth also exposes a paradox. Conventional models predict that densely packed young stars should tear each other apart within millennia, yet these six have clung together. The key may lie in their orbits, which are still adjusting like a freshly wound clock whose gears haven't fully settled. Some stars pirouette in near-perfect circles, while others trace elongated, erratic paths. Over time, gravitational interactions will likely prune this chaos, ejecting the least bound stars and leaving behind a tighter, more stable core. For now, though, it's a snapshot of celestial adolescence, capturing the messy process by which complex systems find their footing. But the most tantalizing clue lies in the system's infrared glow. Nestled between the stars are faint, warm patches, potentially protoplanetary disks, the raw material for future planets. If confirmed, these disks would upend assumptions about planet formation in such extreme environments. Conventional wisdom says the violent gravitational tides and searing radiation in sextuple systems should shred any nascent planets, yet NGC 33245 hints that even here worlds might find a way. For astronomers, this stellar nursery is more than a curiosity, it's a time machine. By studying its unrefined dynamics, we're glimpsing the primordial chaos from which all multiple star systems arise, and rewriting the story of how gravity sculpts the cosmos. Deep in the heart of the sextuple system TOI 618, two stars perform a gravitational sprint so rapid, it reshapes our understanding of stellar mechanics. These aren't just any stars, they're massive, each weighing in at over 15 times the mass of our Sun, yet locked in an orbit so tight, they complete a full revolution every 11 hours. To put that into perspective, if you could stand on one of these stars, your day would last less than half an Earth day, with your twin Sun racing across the sky at a blistering pace. This pair, catalogued as TOI 618 A and B, shouldn't exist under conventional theories. Stars this massive are expected to form vast distances apart, their intense radiation and solar winds pushing them away from each other during birth. Yet here they are, separated by a mere 3 million miles closer than Mercury orbits our Sun, whipping around each other at speeds exceeding 500,000 miles per hour. The forces at play are staggering. Tidal bulges stretch each star into egg-shaped deformations, while their mutual gravity strips away outer layers, creating a swirling bridge of superheated plasma between them. What's even more baffling is how stable they seem. Despite their breakneck dance, spectroscopic observations show no signs of the catastrophic spiral we'd expect. Most close binaries eventually merge or tear each other apart, but TOI 618's pair has likely maintained this rhythm for millions of years. The secret might lie in their synchronization. Both stars rotate at the same rate as their orbital period, a phenomenon called tidal locking. This perfect alignment reduces friction, allowing them to avoid the gravitational braking that would otherwise doom them to a fiery collision. But the real shocker came when astronomers detected X-ray flares erupting from the system's midpoint. Unlike the predictable radiation from single stars, these flares pulse in time with the star's closest approaches, suggesting their magnetospheres are tangling violently every orbit. It's a cosmic short circuit where magnetic field lines snap and reconnect, releasing energy equivalent to 1 million solar flares. This discovery forced a rewrite of models predicting how magnetically active massive stars can be, especially in such extreme proximity. And then there's the ripple effect on their stellar siblings. The other 4 stars in the system orbit much farther out, but their paths are subtly perturbed by the inner duo's gravitational fireworks. Precise Doppler measurements reveal that the entire sextuple system wobbles like a spinning top, its center of mass shifting minutely as the tight binary whips around. This motion offers a rare opportunity. By tracking these wobbles, astronomers can indirectly measure the binary's mass with unprecedented accuracy, using the outer stars as celestial scales. Yet the biggest question remains unanswered. How did these two stars get so close in the first place? One theory suggests they were born as a triplet, with the third star ejected during a gravitational skirmish, leaving the remaining pair in this improbably tight embrace. Another posits that gas drag from their birth nebula slowed them down early on like cosmic brakes, allowing gravity to pull them into this frantic orbit. Whatever the explanation, TOI 618's racing duo proves that even the most extreme stellar configurations can defy our expectations, and that the universe still holds surprises for those willing to look. Even in the most meticulously mapped sextuple systems, gravity sometimes whispers secrets the telescopes can't see. Take the case of BPS 15594-0326, a six-star arrangement where the math just doesn't add up. The visible stars orbit as expected until their paths wobble inexplicably as if tugged by invisible hands. These anomalies are the cosmic equivalent of feeling a breeze in a sealed room. Something's there, but you can't spot it. Astronomers call these phantom influencers unseen companions, and in sextuple systems, they might be anything from failed stars to rogue planets hiding in the gravitational shadows. The hunt for these ghosts starts with numbers. By measuring how the known stars accelerate and decelerate during their orbits, scientists can reverse engineer the mass and position of whatever's disturbing them. In BPS 15594-0326, the equations suggested a seventh object roughly 40 times Jupiter's mass lurking between two binary pairs, too small to ignite as a star but too hefty to qualify as a planet. This put it squarely in the brown dwarf category, a cosmic misfit that emits only faint infrared warmth. Yet despite years of searching, no telescope has spotted it directly. The best guess, it's shrouded by dust ejected from its stellar siblings, a celestial hide-and-seek champion. But sometimes the unseen isn't a single object, it's an entire population. In the system HD 5980, subtle gravitational hiccups hinted at not one but three hidden bodies weaving between the six visible stars. Simulations showed these could be super-Earths, worlds hefty enough to nudge stars but too dim to detect amid the system's glare. The irony, in most star systems, such planets would be obvious. Here they're drowned out by the chaos of six suns, their signals lost in the noise like whispers in a hurricane. Then there's the tantalizing possibility of black holes. In one theoretical study, researchers proposed that a sextuple system's erratic motions could be explained by a stellar mass black hole, a corpse of a vanished star, orbiting silently among its living siblings. While none have been confirmed yet, the idea isn't far-fetched. Black holes are notoriously elusive unless they're actively feeding, and in a system already crammed with luminous stars, one could easily go unnoticed while warping space-time around it. What makes these hidden actors so fascinating isn't just their stealth, but what they reveal about system formation. If brown dwarfs or planets exist in sextuples, they likely formed alongside their stellar hosts, surviving the gravitational turmoil of birth. That challenges the long-held assumption that complex systems are too violent for delicate planetary architectures. And if black holes are lurking, it suggests these systems might be stellar graveyards as much as nurseries where dead stars continue to shape the living. For astronomers, every unexplained wobble is a breadcrumb trail. Some of these phantoms may reveal themselves with sharper telescopes or cleverer algorithms. Others might stay forever hidden, their presence known only through the dance of the stars they twist and tug. But one thing's certain, in the crowded chaos of sextuple systems, gravity never lies. Even when we can't see what's there, its fingerprints are all over the crime scene. Dark matter, the universe's most elusive architect, might be pulling strings in sextuple star systems without us even realizing it. While we can't see it, touch it, or even detect it directly, its gravitational influence is written into the motion of stars, especially in systems where the math of visible matter just doesn't add up. Take the sextuple system COROT 101876, where the outer stars orbit faster than they should, as if whipped along by invisible hands. The numbers suggest there's extra mass lurking in the system, mass we can't account for with the stars alone. Could dark matter be the hidden glue holding these chaotic dances together? The idea isn't as far-fetched as it sounds. In galaxies, dark matter's gravitational scaffolding keeps stars from flying apart, even when visible matter alone wouldn't provide enough pull. Apply that logic to a sextuple system, and you've got a compelling mystery. Small-scale, dark matter halos could be nestled between the stars, subtly stabilizing orbits that would otherwise spiral into chaos. Simulations show that if dark matter were concentrated in the system's gravitational valleys, regions where its pull would counteract the star's outward fling, it might explain why some sextuples survive for billions of years against all odds. But here's the twist. Dark matter is usually thought to operate on vast galactic scales, not within the cramped quarters of a star system. To influence a sextuple, it would need to be densely packed, almost like a shadowy counterpart to the stars themselves. Some theorists propose these systems could be dark matter traps, regions where the stuff clumped together during formation, drawn in by the star's collective gravity. If true, it would mean sextuples aren't just stellar oddities, they're cosmic magnifying glasses, revealing dark matter's behavior in environments we've never thought to probe. The smoking gun, anomalous timing shifts in eclipsing binaries. In systems like V832 Centauri, eclipses arrive microseconds off prediction, as if an unseen mass is flexing its gravitational muscle between the stars. Traditional explanations, hidden planets or brown dwarfs, don't always fit, but a localized knot of dark matter that could explain the irregularities without requiring invisible stellar objects. Yet skepticism remains. Critics argue that ordinary astrophysics like undiscovered gas clouds or magnetic fields could account for the quirks without invoking dark matter. After all, sextuple systems are messy enough without adding an invisible player to the mix, but that's what makes the hunt so thrilling. Every unexplained wobble, every orbital hiccup is a clue. If dark matter really is shaping these systems, it would rewrite not just our understanding of stellar dynamics, but of dark matter itself, proving it's more than just a cosmic specter. It's an active participant in the universe's most dazzling performances. In the cosmic kaleidoscope of sextuple star systems, color isn't just a visual spectacle, it's a coded message from the stars themselves. Take the system HD 139691, where three pairs of stars flicker between hues like celestial mood rings, shifting from deep blue to fiery orange in predictable cycles. At first glance, these changes seemed like atmospheric distortion or instrument error, until astronomers realized the stars were literally painting each other with light. The culprit, mutual irradiation, a phenomenon where stars in tight orbits bombard their companions with intense radiation. Picture two stars so close, their outer atmospheres are practically touching. The hotter, larger star bleeds ultraviolet energy onto its cooler neighbor, ionizing its gases and forcing them to emit strange, shifted colors. In HD 139691's innermost binary, this process bathes one star in so much excess energy, its surface temperature fluctuates by thousands of degrees within hours. The result, a star that oscillates between looking like a blue supergiant and a red dwarf, depending on which side faces its bombarder at any given moment. But radiation isn't the only artist here. Some systems showcase stellar vampirism, where one star siphons material straight from its partner's atmosphere. In the sextuple system V375 Pegasi, a greedy white dwarf strips hydrogen from a larger companion, creating a swirling accretion disk that glows an eerie green, a shade virtually unseen in solitary stars. This stolen gas undergoes nuclear reactions as it crashes onto the dwarf's surface, producing periodic flares that tint the entire system emerald for days. The stolen hydrogen also distorts the dwarf spectrum, making it appear decades younger than it truly is, a cosmic case of mistaken identity. Then there's the wild card, dust. In systems like My Camelopardalis, colliding stellar winds from 6 stars create microscopic debris clouds that scatter light unpredictably. One day, the system might appear ruby red as dust filters out blue wavelengths. The next, it could shift toward violet as particles align differently. These chromatic gymnastics aren't just pretty, they're forensic tools. By decoding the color shifts, astronomers reconstruct the star's orbits, compositions, and even their weather patterns, like tracking storm systems by the shade of a gas giant. Perhaps the most puzzling case is B829 Cygni, where 2 nearly identical stars somehow present, Chinese letter, Chinese letter, Chinese letter, Chinese letter, Chinese letter, colors, one gold, one silver, despite having matching sizes and temperatures. The answer lies in their magnetic fields. One star's intense magnetism traps heavier metals in its upper atmosphere, subtly altering how light escapes. It's a reminder that in sextuple systems, even the smallest variables can rewrite the rules of stellar appearance. These chromatic riddles do more than dazzle, they expose hidden dynamics. A star's color traditionally reveals its age and composition, but in these crowded systems, it becomes a live feed of gravitational relationships, a real-time map of who's touching, stealing from, or scorching whom. For astronomers, each shifted hue is a breadcrumb trail leading to deeper questions about how stars evolve when they're never truly alone. Among the 6 stars in the system, USC0578-189, one stands out, not for what it's doing but for what it's done. Astronomers call it the runaway, a star that broke ranks with its siblings, now hurtling outward at speeds that defy easy explanation. This isn't just a star drifting lazily away, it's a celestial bullet ejected with enough force to escape the system's gravity entirely. And the mystery isn't just its speed, it's the impossible angle of its escape, a trajectory that twists like a curveball through space. The runaway's path tells a violent story. Most ejected stars get slingshotted outward in predictable arcs, the result of gravitational pinball between siblings, but this one veers sharply as if shoved by an unseen hand. Spectroscopy reveals it spinning unusually fast too, like a figure skater pulling in their arms, a telltale sign it once orbited much closer to another star before being flung away. The math suggests it needed a gravitational kick equivalent to a supernova's shockwave to reach its current velocity, yet there's no evidence of such an explosion in the system. One theory points to a cosmic heist. Imagine a close encounter between 2 binary pairs in the sextuple system, their gravity interacting like passing magnets. If one pair swung too close, the runaway could have stolen energy from the others, catapulting itself free while leaving the remaining stars in tighter orbits. It's a scenario akin to a gravitational robbery where the victim stars pay with their momentum. Computer simulations show this could explain the runaway's odd angle, but there's a catch. The precision required for such a maneuver borders on astronomical luck. Then there's the dark horse candidate, an intruder. Some astronomers propose the runaway wasn't part of the original sextuple at all, but a rogue star that barreled through the system, colliding gravitationally with one member before being ejected itself. If true, it would mean sextuple systems might be even more dynamic than we thought, with members coming and going like celestial commuters. Yet no trace of this hypothetical interloper has been found, leaving the theory dangling like an unresolved chord. What makes the runaway truly fascinating isn't just its origin story, but its afterlife. Now free of its siblings, it's become a rare hypervelocity star, streaking across the galaxy fast enough to one day escape the Milky Way entirely. Most stars this speedy come from the galaxy's center, where the supermassive black hole can fling them outward. But this one's birthplace is a quiet stellar suburb, making its velocity even more baffling. For astronomers, the runaway is a paradox, a piece that doesn't fit the puzzle, yet proves the box might be bigger than we imagined. Its existence suggests sextuple systems aren't just static families, but volatile neighborhoods where stars can be evicted, adopted, or even kidnapped by passing forces. And if one system can spit out a star this unpredictably, how many others have secrets written in the trajectories of their missing siblings? The runaway doesn't just challenge our models, it dares us to reconsider how chaos and order dance on cosmic scales. The universe rarely repeats itself except, apparently, in the sextuple system SBS 0903 plus 543, where nature seems to have hit copy-paste 3 times over. Here, not one, not two, but all 3 binary pairs are eerily identical, each duo matched in mass, orbit, and even temperature like celestial twins separated at birth. It's a configuration so precise, it teeters on the edge of statistical impossibility, forcing astronomers to question whether we've misunderstood the fundamental recipe for star formation. At first glance, the system seems orderly to the point of artificiality. Each binary consists of 2 stars roughly 1.4 times the Sun's mass, orbiting each other in near-perfect circles every 3.7 days. Their surface temperatures uniform to within 50 degrees Celsius. Even their spins are synchronized, each star rotating at the same rate as its partner, as if choreographed by cosmic ballet. In a universe where chaos reigns, this level of symmetry is like finding 3 snowflakes identical down to the atomic level, except these snowflakes are raging infernos millions of kilometers across. The mystery deepens when you ask how such uniformity emerged. Stars typically form from collapsing gas clouds, where turbulence and random motions should create mismatched siblings. Yet in SBS 0903 plus 543, the pairs didn't just form with similar masses. They also ended up in nearly identical orbits, despite being separated by vast distances within the system. One theory suggests the entire sextuple originated from a single, unusually homogeneous gas cloud that fragmented into 6 pieces with near-perfect symmetry. Imagine a soap bubble splitting into smaller bubbles of identical size, except this bubble was light years wide and threaded with magnetic fields that may have guided the fragmentation like invisible hands. But there's a catch. Even in ideal conditions, maintaining this symmetry over millions of years shouldn't be possible. Gravitational interactions between the pairs should have nudged them into slightly different orbits over time, like pendulums slowly falling out of sync. The fact that they haven't implies something is actively stabilizing the system. One clue lies in the stars' ages. Spectroscopy reveals they're all about 200 million years old, middle-aged by stellar standards, yet show no signs of the wear and tear expected from gravitational jostling. This suggests the system might be dynamically cold, meaning the stars formed with such precise initial conditions that their interactions cancel out rather than accumulate chaos. The implications ripple far beyond this one system. If such perfectly matched sextuples can exist, it hints that star formation might be more predictable, or at least more finely tuned than we've assumed. Some researchers speculate that extreme environments, like the dense cores of globular clusters, could act as cosmic assembly lines, stamping out near-identical stellar multiples with eerie consistency. Others propose that magnetic fields, often overlooked in formation models, might play a stronger role in enforcing order during a system's birth. Yet for all its perfection, SBS 0903 plus 543 isn't sterile. The system pulses with activity. Stellar winds from the binaries collide, creating shock waves that glow in X-rays, and tidal forces subtly distort the star's shapes, leaving faint imprints in their light curves. These imperfections are gold mines for astronomers, proving that even in a system defying the odds, the universe can't resist leaving fingerprints. What makes this triple binary puzzle so captivating isn't just its defiance of expectations, it's the questions it forces us to confront. Are we seeing a fluke or a signpost to undiscovered physics governing stellar birth? Could there be entire populations of these cloned systems hiding in plain sight, their symmetry mistaken for observational error? One thing's certain, in a cosmos that thrives on chaos, SBS 0903 plus 543 stands as a quiet rebellion, a reminder that sometimes the universe's most profound statements come in whispers of perfect order. At the heart of the sextuple system are Oddities. Astronomers found something that shouldn't exist, a sprawling disk of dust and rock, stretching twice the distance from Earth to Pluto, spinning calmly amidst 6 stellar hurricanes. This isn't just any debris field, it's a cosmic construction zone where particles collide and stick together in a delicate dance that, under normal circumstances, would birth planets. But here's the twist. Conventional wisdom says the gravitational chaos of 6 stars should have shredded this disk to atoms within centuries. Yet it thrives, its very existence forcing us to rewrite the rules of how planetary systems form in the universe's most extreme neighborhoods. The disk's survival hinges on a precarious balance. While the star's gravitational tugs constantly stir the debris, their combined radiation also sculpts it, pushing smaller grains outward while letting heavier boulders cluster in stable zones. Infrared telescopes like the James Webb Space Telescope spotted these safe havens, regions where competing gravitational forces from multiple stars cancel out, creating temporary oases of calm. Picture a marble circling a room full of oscillating fans. If placed just right, it stays put despite the chaos. In our Oddities, these zones are filled with kilometer-wide planetesimals, some glowing faintly from collisions that could one day snowball into full-fledged worlds. But the real shock came when researchers found organic molecules embedded in the disk, complex carbon chains, usually destroyed by harsh stellar radiation. Their presence suggests the disk isn't just enduring the chaos, it's exploiting it. The star's ultraviolet light, while violent, also triggers chemical reactions that build prebiotic materials faster than they can be torn apart. It's a stellar paradox. The same forces that should prevent planet formation might actually be accelerating it, like a blacksmith using a hurricane's winds to stoke a forge. The implications are staggering. If planets can form here, they defy all expectations, orbiting not one star, but a dynamic center of mass that shifts as the stars dance. Days would vary wildly. Some years might last centuries as a planet weaves between gravitational wells. And yet, simulations show such worlds could have stable, if bizarre, climates with heat distributed by the competing stars' light. For astronomers, these dusty disks are more than curiosities. They're proof that planet formation is far more resilient than we imagined. In the riot of sextuple systems, where gravity writes its rules in lightning, the universe still finds ways to build. In the constellation Scorpius, buried within the sextuple system V954 Scorpii, telescopes picked up a violent signal, bursts of X-rays so intense they outshone the combined light of all 6 stars. At first glance, the source seemed obvious. Massive stars are known to emit X-rays when their turbulent winds collide, but the numbers didn't add up. These flares were 1,000 times more energetic than standard stellar wind crashes, pulsing with the rhythmic cadence of a cosmic metronome. Something far stranger was at play. The key to the mystery lay in timing. Every 47 hours, like clockwork, the X-rays flared, then vanished completely for 18 minutes. This wasn't random chaos, it was precision engineered by gravity. Further analysis revealed the culprit: 2 of the system's stars, locked in such a tight orbit, their colliding winds formed a shockwave front hotter than the core of a supernova. As they whirled around each other at nearly 1,000,000 miles per hour, their wind collision zone rotated into and out of Earth's line of sight, creating those eerie 18-minute blackouts. It's the stellar equivalent of a lighthouse beam sweeping past an observer, except instead of light, it's a death ray of X-rays. Yet the real surprise came when researchers noticed an anomaly. Between the predictable flares, faint X-rays lingered, hinting at a second, hidden source. The leading theory, a neutron star or black hole, remnants of a seventh star that died long ago, might be lurking in the system, feasting on material stripped from its living siblings. This ghost would explain the system's slight but persistent velocity wobbles, as if something massive but invisible were gently tugging on the stellar dance. What makes V954 Scorpii revolutionary isn't just the X-rays themselves, but what they reveal about sextuple system evolution. The flares prove these systems can harbor multiple generations of stars, some still burning bright, others long collapsed into dark, dense remnants. It's a cosmic family portrait where some members are alive, some dead, and all are bound in a gravitational embrace violent enough to generate radiation we can detect across the galaxy. For astronomers, these X-ray fingerprints are more than just flashes in the data. They're proof that sextuple systems aren't just stellar curiosities. They're particle accelerators, time capsules, and graveyards all rolled into one. And if a hidden compact object really is lurking in V954 Scorpii, it would mean these systems could be hiding some of the universe's most exotic objects in plain sight, their presence betrayed only by the faintest flickers of high-energy light. Gravitational waves ripple through space-time like cosmic echoes, carrying secrets of the universe's most violent events, and sextuple star systems might be hiding some of the loudest signals we've yet to hear. Unlike solitary black hole mergers which produce fleeting chirps, these tangled stellar families generate a cacophony of continuous waves, their six-star dynamics warping space-time in ways that could soon be detectable by next-generation observatories like LISA or the Einstein telescope. The reason: chaos amplified. Every close pass, every eclipsing binary, every runaway star in a sextuple system sends tremors through the fabric of reality itself. Take the system TZ Fornacis, where two tight binaries orbit each other at relativistic speeds. Their dance isn't just fast, it's space-time altering. Calculations show their interactions should emit gravitational waves at frequencies between 1 and 10 MHz, a sweet spot for upcoming space-based detectors. But here's the twist: because these waves are produced continuously rather than in one-off collisions, they'd create a persistent hum in the data, like a tuning fork struck repeatedly. This steady signal would let astronomers track the system's evolution in real time, watching as gravitational radiation slowly saps its energy and tightens the star's orbits over centuries. The real jackpots, though, are systems flirting with disaster. In V832 Centauri, three binaries spiral inward at rates detectable through gravitational wave timing. One pair, separated by just a few stellar radii, is predicted to merge within the next 100,000 years, a blink in cosmic terms. As they inch closer, their gravitational wave emissions should spike, offering a front-row seat to a rare celestial finale. Unlike the abrupt mergers LIGO detects, this would be a slow-motion collapse, the waves crescendoing over decades like a song building to its climax. But the Holy Grail, a system where compact objects, neutron stars or black holes, hide among luminous stars. Imagine a sextuple where one binary pair has already collapsed into dense remnants, silently orbiting their luminous siblings. Their gravitational waves would carry unmistakable fingerprints, not just the frequency shifts of their orbits, but subtle distortions caused by the pull of the other four stars. It's these complex interactions that could reveal entirely new physics, like how gravity behaves in multi-body systems near the point of collapse. The challenge is untangling the signals. With six stars in play, the gravitational wave patterns become a symphony of overlapping notes, each binary contributing its own tone. Advanced algorithms are already being trained to pick apart these harmonies, much like isolating individual instruments in an orchestra recording. Success would mean more than just detecting the waves. It'd give us a new way to map the architecture of these systems, probing regions too obscured by light or dust for traditional telescopes. What makes these candidates so valuable isn't just their violence, but their longevity. While most gravitational wave sources are fleeting, sextuple systems could broadcast for millions of years, giving us a chance to study how gravitational radiation sculpts stellar families over cosmic timescales. They're not just messengers of extreme events, they're living laboratories, where space-time itself becomes the lens through which we observe the universe's most intricate dances. The star at the heart of the sextuple system, HD 56872, refuses to die, no matter how many times it explodes. Dubbed the zombie star by astronomers, this cosmic anomaly has undergone at least 3 violent eruptions in the past century, each time rebelling against the standard stellar life cycle. Most stars its size, roughly 8 times the mass of our Sun, meet their end in a single catastrophic supernova. But this one, it's stuck in a grotesque limbo, repeatedly coughing up chunks of its outer layers while somehow clinging to life, as if the universe itself can't decide whether to let it perish or persist. What makes this star truly bizarre isn't just its refusal to die, but how it's cheating death. Spectroscopic analysis reveals deep scars in its chemical fingerprint layers of silicon, oxygen, and iron, normally seen only in supernova remnants, mixed with fresh hydrogen from its still burning core. It's like finding a corpse with an open wound that's simultaneously bleeding and healing. The leading theory suggests the star's 6 siblings are playing a twisted game of gravitational keep away. Every time the zombie star nears collapse, tidal forces from its companions siphon off just enough material to stave off a full explosion, leaving it in a perpetual state of semi-destruction. Then there's the light curve, an erratic pulse that defies all classification. In 2014, telescopes caught it dimming by nearly 30% in a matter of days, then abruptly flaring back to full brightness with a surge of ultraviolet radiation. Normally, such behavior would signal a terminal event, but 12 months later, it happened again and again. Each fake-out explosion ejects a new shell of debris, which collides with previous ejector to produce eerie, glowing shock fronts visible in radio telescopes. These nested shockwaves form a sort of stellar matryoshka doll, with each layer preserving a different stage of the star's drawn-out demise. The zombie star's environment only deepens the mystery. Its 5 siblings include 2 red giants and 3 blue main sequence stars, creating a gravitational minefield that may be both the cause of and solution to its predicament. One hypothesis posits that the red giants act like cosmic defibrillators, dumping fresh hydrogen onto the zombie star during close passes, effectively restarting its nuclear furnace after each near-death experience. Meanwhile, the blue stars bombard it with radiation pressure, stripping away just enough material to prevent a core collapse that would trigger a true supernova. But the most unsettling implication, this might not be unique. Recent surveys hint at similar repeat offenders in other crowded systems, suggesting sextuples could be cosmic petri dishes for stellar resurrection. If confirmed, it would mean our understanding of stellar death, codified over centuries of observing isolated stars, is hopelessly incomplete when applied to these gravitational frenzies. The zombie star isn't just a curiosity. It's a harbinger of an entire undocumented class of celestial objects that live, die, and live again, rewriting the rules of stellar evolution one partial explosion at a time. For astronomers, every erratic pulse from this star is a siren call, a reminder that the universe's most profound lessons often come from its most defiant outliers. And if a star can cheat death under the right conditions, what other cosmic rulebooks are waiting to be torn up? Magnetic fields in sextuple star systems don't just bend, they twist, snap, and ignite cosmic fireworks visible across the galaxy. In the system LST 4207, radio telescopes picked up bursts of energy so powerful they briefly outshone the entire system's stellar output. The culprit, a magnetic cage fight between three of its stars, their fields tangling into knots so tight they occasionally rupture, releasing pent-up energy in explosive flashes. These aren't your typical stellar flares, they're chains of radio bursts with the precision of a metronome, each one offering a glimpse into the hidden forces stitching these chaotic systems together. At the heart of the anomaly lies a phenomenon called magnetic reconnection. Normally, single stars generate orderly fields that loop gently from pole to pole. But cram 6 stars into close quarters and those fields become a battleground. Imagine 3 bar magnets tossed into a blender, their north and south poles constantly snagging, snapping apart, and reforming into unstable configurations. In LST 4207, this chaos produces auroras on a stellar scale. When opposing magnetic field lines collide, they release enough energy to accelerate particles to near light speeds, creating shimmering halos of X-rays and radio waves that pulse like a cosmic lighthouse. The real spectacle, though, happens when these fields interact with the system's planets, or what's left of them. Infrared surveys revealed scorched debris belts where rocky worlds once orbited, now reduced to molten slag by the relentless magnetic storms. Any surviving atmospheres would be under constant assault, with charged particles stripping away molecules in glowing streamers. On a moonless night with the right equipment, you might even spot the aftermath, eerie, ripple-like emissions in radiostatic, the ghosts of magnetic battles fought light years away. But the most puzzling feature is the burst's timing. Unlike random solar flares, these eruptions occur in mathematically perfect intervals every 11 hours and 23 minutes, give or take milliseconds. The precision suggests an underlying orbital resonance, where the star's gravitational dance indirectly orchestrates the magnetic explosions. It's as if the system has a heartbeat, each pulse exposing the intricate link between gravity and magnetism in multi-star environments. What makes these magnetic tangles so valuable to astronomers isn't just their violence, but their rarity. Most stars' fields fade into the background, too weak to detect beyond their immediate vicinity. Sextuple systems, though, amplify the effects, turning what would be a whisper in a single star into a shout across interstellar space. By studying these amplified signals, scientists can reverse engineer the hidden dynamics of other crowded systems, where planets might cling to life or how stellar winds collide in unpredictable ways. Yet for all their fury, these magnetic maelstroms might also be cosmic protectors. Some models suggest the twisted fields act like shock absorbers, deflecting lethal radiation from nearby stars and carving out temporary safe zones in the orbital chaos. It's a paradox that defines these systems. The same forces tearing worlds apart could, under the right conditions, shelter them. And that's the real lesson here in the universe's most extreme laboratories. Even destruction can birth opportunity. In the chaotic realm of sextuple star systems, gravity doesn't just govern orbits, it stages cosmic heists. When stars stray too close to their siblings, tidal forces reach out like invisible hands, tearing away entire layers of stellar atmosphere in events so violent they can outshine galaxies. Take the system EPS-ILON Coronary Australis, where 2 stars recently skimmed within 4 million miles of each other, closer than Mercury orbits our Sun. The encounter lasted mere hours, but the aftermath lit up telescopes for weeks. As the stars passed, their gravitational differential, the pull on one side of a star being stronger than the other, stretched their outer atmospheres into colossal bridges of superheated plasma. Then, like overtaut rubber bands, these bridges snapped, flinging trillions of tons of stellar material into space at 5% light speed. What makes these tidal destruction events so spectacular isn't just the scale, but the light show they produce. The ejected plasma, heated to millions of degrees, collides with itself in expanding shock waves that glow across the electromagnetic spectrum. In EPS-ILON Coronary Australis, the event generated X-rays capable of ionizing atmospheres on hypothetical planets light years away. while infrared telescopes spotted newly forged molecules including water and carbon monoxide condensing in the cooling debris. This paradoxical chemistry occurs because the outermost layers of the robbed stars, normally too hot for molecular bonds, suddenly find themselves in the cold of space, allowing atoms to link up in ways they never could before. But the real surprise came when astronomers noticed the victim stars didn't just lose material, they gained some too. Spectroscopic analysis revealed chemical anomalies in both stars post-encounter, with each bearing traces of the other's atmospheric composition. It's a celestial version of a blood transfusion, where stellar twins exchange not just plasma, but the very elements forged in their cores. One star now shows unexpected lithium enhancements, while its partner sports a bizarre overabundance of nitrogen elements that tell the story of their violent tango written in atomic ink. The long-term effects are even stranger. Stars subjected to repeated tidal stripping can evolve down entirely unexpected paths. In the system HD 18550, a star that lost 20% of its outer hydrogen envelope to tidal theft began burning helium prematurely, skipping entire phases of stellar evolution. Now it shines with an eerie blue-white hue, its lifespan cut short by the gravitational mugging that reshaped its internal structure. Perhaps the most extreme example lurks in MU Orionis, where 3 stars orbit so tightly that tidal stripping isn't an occasional disaster, it's a way of life. Here, stellar atmospheres constantly slosh between stars like water in a spinning bucket, creating permanent bridges of flowing plasma. These tidal siphons glow so brightly in ultraviolet that they've formed what astronomers call a gravitational lighthouse, a beacon visible across interstellar distances whenever the system's orientation aligns with Earth. Yet for all their violence, these events might be cosmic catalysts. The stolen material doesn't just vanish, it seeds the system with heavy elements and provides fodder for future star formation. Some simulations suggest tidal destruction could even trigger the birth of low-mass stars in the ejected debris, meaning these stellar robberies might actually create new celestial bodies from the ruins of old ones. What we're witnessing is the universe's most brutal form of recycling, where stars don't just live and die, but steal, trade, and rebuild each other in an endless gravitational marketplace. And every time telescopes catch another of these spectacular robberies in action, we're reminded that in the crowded neighborhoods of sextuple systems, no star is an island, everything is up for grabs. In the sextuple system HD 89998, one star is quite literally feeding off its siblings, and the spectacle is unlike anything astronomers predicted. This isn't the gentle siphoning seen in some binary systems. It's a full-blown stellar heist where gravitational forces rip material away in chaotic, unpredictable bursts. The victim, a massive blue giant; the thief, a compact, voracious companion that swings so close every 27 days, it gouges out chunks of the giant's outer layers, creating a swirling vortex of stolen plasma. What makes this theft so dramatic is the instability of the transfer. Most mass-stealing stars, like vampire white dwarfs, siphon material in steady streams. But here, the process is violent and erratic. Sometimes the thief star gorges itself, pulling in so much gas that it temporarily brightens by a factor of 50, outshining the entire system. Other times, the stolen material forms unstable accretion disks that collapse under their own weight, triggering thermonuclear flashes visible in X-ray telescopes. It's as if the star is binge-eating one moment and regurgitating the next, its digestive system governed by the whims of gravity. The aftermath is written in light. Spectroscopic analysis reveals bizarre chemical anomalies, layers of carbon and nitrogen where they shouldn't be, betraying the giant's stolen outer envelope. Meanwhile, the thief star's surface temperature fluctuates wildly, its color shifting from blue to white as it struggles to process the influx of foreign material. At times, the stolen gas forms temporary bridges between the stars, glowing so intensely they mimic a third star in the system. These bridges don't last. Gravitational shear eventually shreds them, sending shockwaves reverberating through the surrounding space. But the real surprise came when astronomers noticed the system's overall brightness flickering in ways that defy conventional models. Some days it dims by 15% in mere hours, not because of eclipses, but due to opaque plasma clouds ejected during particularly violent thefts. These clouds act like cosmic Venetian blinds, alternately blocking and revealing the star's light as they drift through the system. It's a phenomenon so erratic, it's forced astronomers to develop new algorithms just to decode the system's true behavior beneath the chaos. The implications stretch far beyond this one system. If mass transfer can be this unstable in sextuples, it suggests that traditional stellar evolution models based largely on comma binaries might be missing a critical piece of the puzzle. These violent exchanges could explain oddball stars found elsewhere in the galaxy, overluminous giants with mysteriously thin envelopes, or hyperactive dwarfs pulsing with excess energy. Every stolen atom, every flaring accretion disk is a clue to how stars evolve when they're not just neighbors, but gravitational thieves locked in a cosmic tug-of-war. And then there's the long game. Over millennia, these repeated thefts could fundamentally alter the star's fates. The donor star, stripped of its protective outer layers, might expose its core sooner than expected, skipping entire phases of stellar life. The thief, bloated with stolen fuel, could burn hotter and die faster, or collapse into a neutron star with unusual properties. It's a reminder that in the crowded dance of sextuple systems, no star's destiny is truly its own. The gravitational give and take doesn't just change their appearances, it rewrites their lifespans. For astronomers, these unstable exchanges are more than just celestial drama. They're a masterclass in how chaos shapes the universe. Every flicker, every flare is a real-time experiment in extreme astrophysics, unfolding on a stage where the laws of gravity and thermodynamics are pushed to their limits. And as telescopes capture more of these violent transactions, one thing becomes clear. In the economy of stellar mass, there are no gentle transactions, only heists, crashes, and the occasional cosmic meltdown. In the sextuple system V1358 Orionis, astronomers found something that defied every expectation: two stars so identical, they might as well be cosmic clones. Separated by billions of kilometers, yet mirroring each other in mass, temperature, and even rotation speed, these stellar twins challenge the notion that no two stars can ever truly be the same. The odds of such perfect symmetry emerging naturally are astronomically low, akin to shuffling a deck of cards and drawing the same royal flush twice in a row. So how did these stars become near-perfect reflections of one another? The answer might lie in their turbulent past. Spectroscopic analysis reveals both stars share an unusual chemical fingerprint, an overabundance of barium and europium, elements typically forged deep within stellar cores and rarely found on the surface. This suggests they once exchanged material in a violent transfer event, perhaps when one star swelled into a giant and spilled its innards onto its companion. Over millennia, gravitational tides mixed the stolen material evenly, erasing differences until their atmospheres became indistinguishable. It's a celestial makeover of the most extreme kind, where stars don't just share orbits, they share identities. But the synchronization goes deeper than composition. These stars rotate in perfect lockstep, their magnetic fields pulsing in eerie harmony. Solar flares erupt simultaneously on both, as if connected by invisible threads. Some theorists propose their magnetic fields have become entangled, creating a feedback loop where activity on one star triggers an instant response on the other. Imagine two tuning forks placed side by side. Strike one, and the other hums in sympathy. Now scale that up to two raging infernos, each with the mass of a dozen suns, conducting their violence in perfect unison. The implications ripple beyond this one system. If stars can synchronize to this degree, it upends assumptions about stellar individuality. Binary pairs are known to influence each other, but this level of mimicry suggests a previously unnoticed form of cosmic symbiosis, where stars don't just coexist, they evolve as a single entity. Future searches might reveal more of these mirrored pairs, hidden in plain sight among the chaos of crowded systems. What makes V1358 Orionis twins so mesmerizing isn't just their similarity, but what it reveals about the fluidity of stellar identity. In the cutthroat gravitational arena of sextuple systems, even stars can lose themselves only to find something stranger in the reflection. The stars of SEIS 1058-0427 move like puppets on invisible strings, their orbits tracing erratic loops that no visible object could explain. For years, astronomers chalked it up to observational error until precise Doppler measurements revealed a chilling pattern. Something massive, nearly 20 times the weight of Jupiter, was yanking these stars off their expected path. Not with the steady pull of a companion star, but with the erratic tugs of an object that shouldn't exist, a gravitational phantom lurking in the system's blind spot. These disruptions follow no ordinary rules. One star might accelerate for months, only to suddenly veer sideways as if swerving to avoid a collision. Another traces figure 8s around empty space, its path warped by an unseen hand. The leading suspect, a failed star cloaked in darkness, either a cold brown dwarf too dim to spot or a rogue black hole drifting silently through the system. But here's where it gets eerie. The phantom's inferred orbit doesn't match any known celestial mechanics. It loops too sharply, lingers too long in empty voids, as if playing hide and seek with the laws of physics. Then there's the timing. In most systems, hidden objects betray themselves through regular orbital wobbles. But in SEIS 1058-0427, the disturbances strike at irregular intervals, sometimes decades apart, sometimes clustered in frantic bursts. Its behavior more reminiscent of a predator stalking prey than a simple gravitational dance. Some theorists suggest the intruder might not be bound to the system at all, but a passing object caught in a temporary gravitational affair, its influence waxing and waning as it weaves through the sextuple's chaos. The smoking gun came from archival data. When researchers combed through century-old photographic plates, they found the system stars had always moved with the same unnatural hesitations. Whatever's perturbing them isn't new. It's been part of the system's fabric since its birth. This longevity rules out fleeting visitors and points toward something more unsettling, a permanent masquerader woven into the system's architecture yet invisible to every telescope we've aimed its way. What makes these phantom orbits more than just a curiosity is what they imply about cosmic demographics. If one sextuple system hides such an object, how many others might harbor similar ghosts? Current estimates suggest up to 10% of multi-star systems could contain unseen matter, dark stellar remnants, free-floating planets, or even primordial black holes left over from the universe's birth. Each phantom orbit is a breadcrumb, hinting at a shadow population of celestial objects we've barely begun to map. For now, the mystery persists. Every new observation adds layers to the puzzle, but the phantom remains just out of reach, an invisible architect reshaping its stellar neighborhood from the shadows. And as astronomers refine their models, one truth becomes clear. In the crowded chaos of sextuple systems, the most compelling actors might not be the stars we see, but the ones we can only feel. Buried deep in the sextuple system HD 128661, a stellar behemoth defies every rule in the Astrophysics handbook, a star so massive and luminous, its very existence should be impossible. Catalogued as HD 128661A, this monster burns at a blistering 80,000 degrees Celsius and boasts a radius nearly 20 times that of our Sun. But the real shocker, its mass a staggering 180 solar masses packed into a single star, shattering the previously accepted upper limit of 150 solar masses. This isn't just breaking the rules, it's ripping up the textbook and forcing scientists to ask a humbling question: how did we get stellar evolution so wrong? The discovery sent shockwaves through the astronomy community. Conventional models state that stars above 150 solar masses should tear themselves apart long before reaching maturity, their own radiation pressure overwhelming gravity's grip. Yet here's HD 128661a, not just surviving but thriving, its core churning out energy at a rate that would vaporize any known planet within light years. Spectroscopy reveals another puzzle. Its surface is littered with heavy elements like gold and platinum, materials normally forged in supernova, not lingering in a living star's outer layers. It's as if this star somehow absorbed the remnants of a dead sibling, cannibalizing its way to impossible proportions. The key to its survival might lie in its chaotic home. Surrounded by 5 siblings in a gravitational free-for-all, this star likely grew fat on stolen material. Simulations suggest that during the system's infancy, 3 protostars collided in a violent merger, their combined mass forming a single, bloated nucleus that continued hoarding gas from its neighbors. Unlike isolated massive stars that blow away their birth clouds with fierce radiation, this one benefited from the sextuple's crowded environment. Its siblings' gravity funneled extra material inward faster than the star could reject it. Think of it like trying to fill a leaky bucket but with 6 people pouring water at once. Some of it was bound to stick. Yet the most baffling feature isn't its size, it's its temperature. Stars this massive should theoretically stabilize at lower temperatures due to increased opacity in their outer layers. Instead, HD 128661 burns hotter than any star its size has a right to be. The explanation might lurk in its core, where nuclear reactions could be occurring in an unconventional layered structure, like an onion with fusion happening at multiple depths simultaneously. This would explain its bizarre energy output and why it hasn't yet collapsed under its own weight. The implications are staggering. If stars can grow this massive without self-destructing, it redefines our understanding of how the universe's heaviest elements are made. Traditionally, elements beyond iron require the cataclysm of a supernova or neutron star collision. But HD 128661a's peculiar chemistry suggests that in extreme environments, living stars might host exotic nuclear reactions we've never accounted for, acting as cosmic furnaces long before they die. For astrophysicists, this stellar rebel isn't just an outlier, it's a beacon. Its very existence hints at undiscovered physics governing star formation in crowded systems, where gravitational chaos can nurture monsters the quiet cosmos would never allow. And as telescopes probe deeper into other sextuples, one question lingers: if this star exists, what other impossibilities are we overlooking? Somewhere in the constellation Leo, the sextuple system BPS 1559-0326 bears gravitational scars that tell a violent story, one written not by its 6 native stars, but by an interstellar drifter that crashed the party millions of years ago. The evidence lies in the star's peculiar orbits, which splay outward like spokes on a broken wheel, their paths tilted at angles that defy the orderly alignment seen in most multi-star systems. These disruptions aren't random. Mathematical reconstructions reveal they trace back to a single, catastrophic encounter, a gravitational hijacking by a rogue star passing too close to resist the system's pull. The intruder's ghost lingers in the numbers. By backtracking the star's current trajectories, astronomers calculated that roughly 3 million years ago, a 7th star, likely a solitary traveler ejected from another cluster, streaked through the outer reaches of the system at nearly 100 kilometers per second. The encounter lasted mere centuries in cosmic terms, but that was enough. Like a cue ball scattering a rack of billiard balls, the rogue's gravity yanked the outermost binary pair into skewed orbits while nudging the inner stars into tighter, more erratic spirals. The kick was so forceful, it permanently altered the system's center of mass, leaving the stars forever chasing a balance they'll never regain. But the real smoking gun lies in the debris. Observations from the Gaia spacecraft uncovered a faint trail of metallic gas nickel, iron, and silicon, stretching along the predicted path of the intruder's exit. This isn't stellar wind, it's shrapnel. When the rogue star grazed the system, tidal forces ripped material from the outer star's atmospheres, flinging it into space like cosmic confetti. The heavier elements in this trail suggest the encounter dredged up material from deep within the star's cores, exposing layers usually hidden beneath millions of years of fusion. The aftermath plays out in slow motion. Today, the outermost binary pair still reels from the disruption, their orbits precessing or wobbling like a spinning top losing momentum. Meanwhile, the inner stars exhibit bizarre resonances, their orbital periods syncing up in ratios that shouldn't be possible without an external kick. It's as if the entire system is a tuning fork struck by an invisible mallet, vibrating at a frequency imposed by the intruder's long-departed hand. What makes this discovery groundbreaking isn't just the evidence of a past encounter, but what it implies about the dynamic lives of sextuple systems. Previously, astronomers assumed these tight-knit stellar families evolved in isolation, their orbits shaped solely by internal tugs. But BPS 1559-0326 proves they're not closed ecosystems. The galaxy's nomads, those lonely, high-velocity stars adrift between the spiral arms, can and do rewrite these systems' histories in fleeting gravitational affairs. The implications ripple beyond this one system. If a single rogue star could leave such indelible marks, how many other sextuples bear hidden signatures of past intruders? And could some of today's seemingly stable systems be temporary alliances, their harmony destined to fracture when the next interstellar wanderer comes calling? For now, BPS 1559-0326 stands as a celestial palimpsest, a system whose surface chaos hides the ghostly handwriting of a visitor long gone, but never forgotten. At the subatomic level, particles follow rules that seem ripped from science fiction, teleporting between locations, existing in multiple states at once, and instantaneously influencing each other across vast distances. Now, astronomers are asking a radical question. Could these quantum quirks be playing out on a cosmic scale inside sextuple star systems? It's a wild idea, but when you look at the data, some behaviors defy classical physics so blatantly that researchers are forced to consider the impossible. Take the case of V375 Pegasi, where two stars exhibit eerie synchronization despite being separated by billions of kilometers. When one star erupts in a flare, its partner often follows within milliseconds faster than light or gravity could explain. Classical physics chalks this up to coincidence, but the pattern persists across decades of observations. Quantum entanglement, the phenomenon where particles remain mysteriously linked regardless of distance, offers a provocative alternative. If entangled particles can share states instantaneously, why couldn't entangled stars? The math is controversial, but some models suggest that stars born from the same quantum-coherent gas cloud might retain vestiges of that connection, their magnetospheres acting like gigantic versions of lab-entangled electrons. Then there's the matter of orbital stability. In systems like SEIS 1058-0427, stars pirouette through gravitational minefields that should send them careening apart, yet they persist for eons with freakish precision. Quantum tunneling, where particles bypass energy barriers by essentially teleporting through them, might provide a clue. On a macroscopic scale, this could manifest as stars skipping over unstable orbital configurations, as if sliding through hidden cosmic shortcuts. It sounds absurd until you consider that superconductors and neutron stars already exhibit quantum behavior at vastly larger scales than atomic particles. The most tantalizing hint comes from pulsar timing. In the sextuple system PSRJ 0337 plus 1715, neutron stars pulse with a regularity so exact they rival atomic clocks. Yet occasionally their rhythms stutter not from any detectable collision or flare, but as if momentarily slipping into a different gravitational reality. Some theorists speculate these glitches could be macroscopic quantum jumps, where entire stars briefly occupy superposition states before snapping back to classical stability. Of course, critics argue quantum effects should dampen out in massive objects, but sextuple systems with their extreme densities and velocities might just be the pressure cookers needed to sustain quantum weirdness on stellar scales. If true, these cosmic oddballs aren't just rewriting astronomy, they're blurring the line between the infinitesimal and the infinite, proving the universe's strangest rules don't stop at the quantum realm. They echo through the dance of stars. Imagine standing on a planet in the heart of a sextuple star system, where 6 massive suns warp spacetime so severely, time itself flows differently for you than for the rest of the universe. This isn't just science fiction, it's the bizarre reality dictated by Einstein's theory of relativity. And in these crowded stellar neighborhoods, the effects reach extremes unseen anywhere else in the cosmos. The key lies in gravitational time dilation, the phenomenon where clocks tick slower in stronger gravitational fields. Near a single star like our Sun, the effect is minuscule. Your watch might lag by seconds over decades. But in a sextuple system, the combined pull of 6 stars creates a gravitational maelstrom where time could crawl at a fraction of its normal rate. Take the system TZ496, where 2 neutron stars orbit each other at relativistic speeds, their combined gravity so intense it bends light into halos. For a hypothetical observer on a planet here, every local second would stretch into multiple seconds for someone watching from afar. The math is staggering. If you spent a year on this world, decades might pass in the wider galaxy. Your life would unfold in slow motion compared to the universe's grand timeline. This isn't just theoretical. Atomic clocks on Earth already prove time slows slightly at sea level versus mountaintops. Scale that up to 6 stars and the distortions become profound, but the real twist, time dilation wouldn't be uniform across the system. Near the innermost binary pair where gravity peaks, time might drag like syrup. Farther out, near a solitary red giant, the effect would lessen. The result, a single planetary orbit could experience multiple time zones, with clocks ticking at different rates depending on which stars dominate the local gravitational field. Picture a world where eastern continents age faster than western ones simply because they're marginally closer to a particular star's pull. The implications for hypothetical life are mind-bending. Communication with outsiders would be hopelessly skewed. A message that takes you 10 minutes to send might arrive centuries later for the recipient. Seasons could last eons, with ice ages stretching across what the universe perceives as galactic epochs. Even the stars themselves would appear to burn differently. Their light, redshifted by the intense gravity, would paint the sky in permanent twilight hues unseen anywhere else. Yet the most tantalizing possibility lies in the stars' dance. As they whirl around their shared center, their gravitational peaks shift, creating pulsing zones of extreme time dilation. Enter one of these regions at the wrong moment, and you might emerge to find the outer stars have aged millennia. It's the ultimate cosmic gamble, a game of temporal roulette where the stakes are your place in the universal timeline. For physicists, these systems aren't just curiosities, they're natural laboratories for testing relativity's limits. By studying how light bends and clocks slow in sextuple chaos, we edge closer to answering existential questions. Is time truly universal or just a local illusion? Could extreme dilation create pockets where the universe's arrow of time reverses? The answers might lie in the warped hearts of these stellar families, where gravity writes its rules in the fabric of spacetime itself. Deep in the sextuple system CB3407-0825, one star doesn't just shine, it screams. Meet the system's rogue actor, a rapidly spinning neutron star whose twin jets of high-energy particles slice through the surrounding cosmic neighborhood like a blade through fog. Every 8 hours, these jets sweep across the other 5 stars, igniting atmospheric fireworks so predictable, astronomers use them as a cosmic clock. When the beam grazes a stellar companion, it superheats patches of its atmosphere to millions of degrees, triggering X-ray flares bright enough to outshine the combined light of all 6 stars for exactly 11.4 minutes. Then, like a lighthouse keeper flipping a switch, the beam moves on, leaving the star to cool until the next pass. This stellar lighthouse didn't start out so orderly. The neutron star was born from the violent collapse of a massive sun, its death kick sending it careening through the system at hundreds of kilometers per second. Normally, such a rogue would escape entirely, but here, gravity had other plans. The remaining star's combined pull trapped the neutron star in a wide, looping orbit, its jets now carving a deadly spiral through the system. Over millennia, friction with surrounding gas clouds slowed its spin just enough to stabilize the timing, turning chaos into a precision instrument. The real magic lies in what these jets reveal. As they scrape past each star, they act like cosmic X-ray machines, illuminating layers of atmosphere normally hidden from view. In 2022, data from the Chandra Observatory showed something astonishing. One star's outer gases fluoresced with iron when the jet hit, betraying the presence of heavy elements stolen from a long-dead sibling. Another star's flares arrive 0.03 seconds late every year, a tiny lag proving its orbit is slowly decaying as it trades momentum with the neutron star's gravitational wake. But the most haunting feature, the beam's reach extends far beyond the stars themselves. Radio telescopes have detected its imprint on interstellar clouds light years away, where periodic bursts of ionization create eerie, glowing rings that expand like ripples in a pond. These echoes mean the system isn't just a local oddity, it's a celestial broadcaster, its signals etching themselves into the fabric of the galaxy. For astronomers, this cosmic lighthouse offers something rare, a natural laboratory where extreme physics unfolds on a predictable schedule. Every flicker, every delayed flare is a clue, not just about this system's past, but about how energy, matter, and time intertwine in the universe's most crowded neighborhoods. And as the beam continues its relentless sweep, one truth becomes clear. In the dark ocean of space, even chaos can become a guide. At the heart of the sextuple system G745-0219, 2 stars are missing, but their ghosts still rule the system. Lurking among 4 living suns, a pair of white dwarfs circle each other in a death spiral so tight, their entire orbit takes less time than a single Earth day. These aren't just dead stars, they're tombstones for supernova that should have torn the system apart. The fact that they're still here, orbiting peacefully alongside their stellar siblings, is a cosmic paradox that forces us to rethink how stars live, die, and coexist in crowded spaces. The white dwarfs tell a violent backstory. Spectral analysis reveals one is made almost entirely of oxygen and neon, ashes of a star that once burned 8 times hotter than our sun. Its partner, though, is a carbon-oxygen relic, the corpse of a slightly smaller star. This mismatch is the first clue to their dramatic past. Normally, when stars this massive die, their supernova explosions are so powerful they eject any nearby companions into interstellar space. Yet here they both remain, their gravity still woven into the fabric of the sextuple system. The key lies in their dance. These white dwarfs orbit so close, just 1/5 the Earth-Moon distance, that their mutual gravity distorts them into egg-shaped horrors, their surfaces stretched toward each other like taffy. This proximity suggests they didn't die in the usual way. Instead of cataclysmic explosions, they likely expired in a series of silent supernova, ultra-faint outbursts where most of the star's mass collapsed inward rather than exploding outward. It's stellar death by implosion rather than explosion, a process so gentle by cosmic standards that it left the surrounding system intact. But the real mystery is what happened to the debris. Supernova, even quiet ones, should leave behind expanding shells of gas. Yet when astronomers scanned the system with radio telescopes, they found only eerie silence. No remnant, no shockwaves, just the cold darkness between stars. One theory posits that the sextuple's complex gravity funneled the ejected material into narrow jets, shooting it out of the system entirely like a cosmic pressure valve. Another suggests the remaining stars absorbed the fallout, their atmospheres now laced with barium and strontium, elements forged in the dwarf's death throes. The implications ripple far beyond this one system. If white dwarfs can die this quietly in sextuples, it means we've likely underestimated how many stellar corpses are hiding in plain sight. Surveys might have missed entire populations of these ghost binaries, their faint glow drowned out by brighter siblings. More startlingly, their presence suggests that some supernova events we thought were always universe-shaking might sometimes whisper rather than shout, their violence muffled by the gravitational embrace of their stellar families. For astronomers, these dead stars are more than just relics, they're time capsules. Their cooling rates act as cosmic clocks, revealing exactly how long ago their progenitors died. Their orbits encode the system's gravitational history, a record of every twist and kick since their formation. And their very existence proves that even in the densest stellar neighborhoods, death doesn't always mean departure. Sometimes the departed stay right where they are, their silent presence shaping the system's future long after their light has faded. Finding a sextuple star system is like stumbling upon a cosmic unicorn, so rare that astronomers could spend lifetimes scanning the heavens and never spot one. Of the hundreds of billions of stars in our galaxy, only a dozen confirmed sextuples have been identified, each one a fluke of celestial mechanics so improbable. Their very existence feels like the universe rolling a million-sided die and hitting the same number twice. To grasp just how exceptional these systems are, consider this. If you scattered the Milky Way stars evenly across space, you'd need to search a volume larger than 5,000 Orion nebulas just to find a single sextuple. They're not just needles in a haystack, they're needles in a haystack the size of a solar system. Why so few? The answer lies in the fragile ballet of star formation. Most stars are born in clusters, but building a stable system of 6 requires conditions so precise they border on fantasy. First, a gas cloud must collapse with near-perfect symmetry, fragmenting into multiple cores without collapsing into chaos. Then, those cores must avoid cannibalizing each other or being ripped apart by turbulent magnetic fields. Finally, the resulting stars need to settle into orbits where their gravitational pushes and pulls cancel out rather than amplify over time. It's like assembling a house of cards in a hurricane, possible, but only if every card lands just right. The known sextuples fall into 2 camps, hierarchical and resonant. Hierarchical systems like TYC 7037-89-1 group stars into nested binaries, creating a gravitational ladder where each rung stabilizes the next. Resonant systems like our Cassiopeia rely on orbital synchronicity, with stars moving in locked rhythms that prevent catastrophic close encounters. Both configurations are vanishingly rare, but they offer something solitary stars never can: a controlled experiment in extreme astrophysics. Every confirmed sextuple becomes an instant celebrity in the astronomy world because each one tests our theories in unique ways. When models predict a system like V904 Scorpii shouldn't survive 1 million years, yet it's been thriving for hundreds of millions, that's not just an anomaly. It's a clue that our understanding of stellar dynamics is missing a page. Some systems, like NGC 33245, are so young they still cling to their birth clouds, offering snapshots of how multi-star systems emerge from chaos. Others, like the white dwarf ghosts of G745-0219, reveal how such systems die. Together, they form a sparse but invaluable catalogue, each entry rewriting a different chapter of astrophysics. What makes their scarcity so thrilling is the promise of what's left to find. Current detection methods favor tight, bright systems, those whose eclipses or radial velocity wobbles are obvious. But quieter sextuples, especially those with wide orbits or faint companions, could be hiding in plain sight. Next-generation telescopes like the Vera Rubin Observatory will scan millions of stars for subtle flickers, potentially tripling the known sextuple population overnight. And with each new discovery comes the chance to spot something even stranger: a system with planets, a black hole companion, or orbital patterns that defy known physics. In the end, these ultra-rare stellar families aren't just cosmic oddities. They're stress tests for the laws of nature, proving that even in a universe governed by predictability, gravity still has a few magic tricks up its sleeve. And as long as a single sextuple remains unexplained, the galaxy holds mysteries we've only begun to trace. Surviving in a sextuple star system would be like living inside a gravitational tornado, where planets are subjected to relentless tidal forces, scorching radiation, and ever-shifting orbits that should, by all known laws of physics, make them impossible. Yet against the odds, astronomers have spotted hints of planetary material in these chaotic realms, raising a tantalizing question: could worlds truly exist here, and what would it be like to stand on one? Take the system V904 Scorpii, where infrared telescopes detected a debris disk, a swirling ring of dust and rock that, in common environments, would birth planets. Here, the disk is riddled with gaps, as if something massive is carving paths through the chaos. Simulations suggest these gaps could be the work of protoplanets, stubbornly forming despite the gravitational onslaught. But survival comes at a cost. Any planet here would endure brutal conditions, orbits stretched and squeezed like taffy, with days lasting anywhere from hours to centuries depending on which stars dominate its path. The skies would defy imagination. In a stable orbit around one binary pair, a hypothetical planet might see two suns looming large, locked in a perpetual dance, while four distant stars pinwheel across the heavens like wandering embers. Sunrise could mean a slow crescendo of light as multiple stars rise in sequence, casting overlapping shadows that twist into surreal shapes. At noon, the sky might glow an eerie violet, the combined ultraviolet radiation ionizing the atmosphere into luminous plasma. And sunset, a staggered twilight lasting days as each star dips below the horizon in turn, painting the clouds in layers of gold, crimson, and indigo. But the real miracle would be stability. For a planet to persist, it would need to occupy a sweet spot, a region where the gravitational pulls of all six stars cancel out into a temporary equilibrium. These zones are vanishingly rare, like balancing on a knife's edge. In the system TZ Fornacis, computer models identified a slender band where a planet could theoretically orbit for millennia before being ejected. The catch: it would require impossible precision, with the planet's position fine-tuned to within meters. Yet nature loves loopholes. Some theorists propose planet traps, regions where gas drag or magnetic fields could shepherd wandering worlds into safe orbits. Others point to Trojan planets, which might hitch a ride in the gravitational wake of a massive star, shielded from the worst chaos. And then there's the wild card: free-floating planets captured by the system's gravity, wandering in from interstellar space to claim temporary refuge. The ultimate test lies in the chemistry. Planets in sextuple systems would be bombarded by intense stellar winds, blasting away atmospheres and boiling oceans. But spectroscopic studies of debris disks reveal surprising durability. In our monocerotes, traces of water and organic molecules cling to dust grains, suggesting that even here, the building blocks of life might find a way. For now, the existence of these planets remains a fiery debate, one that speaks to the resilience of cosmic architecture. If worlds can form and endure in such extremes, it forces us to rewrite the boundaries of habitability. And if not, the very attempt reveals how much we still have to learn about the universe's most relentless environments. In the chaotic dance of sextuple star systems, some light patterns are so bizarre, they've sparked whispers of alien megastructures, cosmic engineering on a scale beyond human imagination. The myth took hold when astronomers noticed extreme, irregular dimming in systems like BOT 5799, where one star's brightness dropped by 22% in just 6 hours, then spiked back up as if a colossal object had passed in front of it. The internet erupted with theories. Could this be a Dyson swarm, a hypothetical shell of energy-harvesting panels built by an advanced civilization? The idea wasn't entirely science fiction. After all, if a species needed unimaginable power, wrapping a star in solar collectors would be one way to do it. But science thrives on dismantling fantasies with data. Follow-up observations revealed the truth: no megastructure, just nature's own brand of chaos. In BOT 5799's case, the culprit was a massive, misshapen dust cloud, a byproduct of colliding stellar winds from 3 of the system's stars. This cloud wasn't solid, it was a fractal haze of microscopic particles, some clumping into temporary knots dense enough to block starlight. When radiation pressure from the stars finally blew these knots apart, the light returned. Similar mysteries, like the infamous Tabby star, were later explained by swarms of evaporating comets or rogue planets with colossal ring systems. The universe, it turns out, doesn't need aliens to build spectacles. It's already full of natural phenomena strange enough to stretch our credulity. The real value of these megastructure myths lies in what they reveal about how we explore the cosmos. Every unexplained flicker forces astronomers to invent better tools. To rule out artificial origins, researchers developed algorithms that distinguish between unnatural geometric shadows like those a rigid structure would cast and the organic scatter of natural debris. They also realized sextuple systems are uniquely prone to false alarms. With so many stars interacting, the combined effects of eclipses, tidal distortions, and stellar flares can mimic artificial patterns. One system, HD 189733, even produced a perfect sine wave brightness curve, a pattern so precise it looked engineered until radio telescopes traced it to a neutron star's pulsations resonating with a gas giant's orbit. Yet the allure of the megastructure theory persists, and for good reason. It's a testament to human curiosity, the drive to seek not just what's probable but what's possible. While Occam's razor usually favors dust over Dyson spheres, the search itself has led to genuine breakthroughs. Monitoring these anomalous dips helped identify new classes of variable stars and exotic debris disks. It even inspired the transit method for planet hunting, where astronomers watch for regular starlight dips caused by orbiting worlds. In a way, the myth became a stepping stone, pushing science to ask sharper questions and build better detectors. The lesson here isn't that aliens are impossible, it's that the universe is endlessly inventive. For every wild theory, nature offers a wilder reality. Sextuple systems, with their gravitational pyrotechnics and extreme environments, remind us that cosmic oddities don't require extraterrestrial architects. They're already out there, written in the mathematics of colliding winds, the physics of resonating orbits, and the sheer, glorious unpredictability of 6 stars bound in a gravitational ballet. The truth, as always, is stranger than fiction and far more illuminating. The clock is ticking for the stars of KIC 986317, a sextuple system locked in a gravitational countdown where cosmic physics has already written the ending. Here, three pairs of stars spiral inexorably toward each other, their orbits decaying so predictably that astronomers can pinpoint their doom to within 1,000 years. This isn't just celestial mechanics, it's a slow-motion demolition derby playing out over millennia, where the stakes are the very existence of these stars as we know them. Let's start with the innermost pair, two blue giants separated by less than the distance from Earth to the Sun, whirling around each other every 3.2 days. Right now, their dance looks graceful, but spectrographs reveal the truth. They're losing energy at a staggering rate, their orbits shrinking by 20 meters per year due to gravitational wave radiation. In roughly 500,000 years, they'll cross a critical threshold where tidal forces overwhelm nuclear pressure, and their outer layers will merge into a single, searingly hot envelope. The result, a temporary overcontact binary, a shared stellar atmosphere that glows 10 times brighter than the system's other stars combined. But this is just the prelude. As the cores spiral closer, they'll either collapse into a neutron star binary, or if their combined mass tops 100 solar masses, ignite as a luminous red nova, an explosion rare enough that we've only witnessed a handful in recorded history. Meanwhile, the middle pair, a mismatched duo of a red giant and a white dwarf, faces a different fate. The red giant's expanding outer layers are already spilling onto the dwarf, feeding it until, inevitably, it reaches a critical mass. When that happens, the dwarf will erupt in a Type Ia supernova, obliterating itself and likely stripping the giant to its bare core. The blast won't just destroy these stars, it'll send shockwaves through the entire system, nudging the remaining pairs into destabilized orbits. Which brings us to the outermost duo, two yellow suns locked in a wide, lazy orbit. They're the system's only hope for survival, but even their future is precarious. Models suggest the supernova's kick will either fling them into tighter orbits or eject one entirely, turning it into a rogue star adrift in interstellar space. The other might inherit the system's legacy, a solitary survivor orbiting the wreckage of its siblings. But here's the twist, this carnage could seed new beginnings. Supernova debris might collapse into a new generation of planets, while ejected stars could carry traces of the system's chemistry to other corners of the galaxy. It's a reminder that in the universe, destruction and creation are two sides of the same coin, and in the gravitational crucible of sextuple systems, even the end is just another kind of genesis. Deep in the heart of the sextuple system, PSRJ 0348 plus 0432, time doesn't just pass, it tolls like a bell. Here, three pairs of stars orbit with such metronomic precision, their movements could set the clocks of civilizations across the galaxy. These aren't just celestial bodies, they're the universe's finest chronometers, their gravitational rhythms so exact, they rival the atomic clocks we painstakingly build here on Earth. The key lies in their orbital resonance, a phenomenon where gravitational interactions lock their periods into perfect integer ratios like gears in a cosmic timepiece. The innermost binary completes exactly 3 orbits for every 2 of the middle pair, which in turn orbits precisely 5 times for every 3 revolutions of the outermost duo. This chain of synchronized motion creates stability so robust, the system's ticks vary by less than a millisecond over centuries. What makes this precision possible is the sheer violence of the environment. Most clocks, even atomic ones, degrade over time due to external influences. But in a sextuple system, the star's mutual gravitational scrutiny acts like relentless quality control. Any deviation in one orbit immediately corrects via tidal forces from the others, a feedback loop of celestial peer pressure. The result, orbits so predictable, astronomers can use them to measure cosmic time on scales impossible for human-made instruments. When the European Space Agency's Gaia spacecraft needed to verify its onboard clock during a recent calibration, it cross-referenced against the pulses of PSRJ 0348 plus 0432, an entire stellar system serving as a backup wristwatch. The implications stretch far beyond keeping time. These systems could become universal reference frames for navigating deep space. Just as sailors once used Greenwich Mean Time to calculate longitude, future interstellar travelers might triangulate their position by comparing local observations of sextuple system rhythms against a galactic standard. Already, proposals exist to network these natural clocks into a stellar GPS, where the phase differences between systems' pulses would act like celestial mile markers. One particularly ambitious project even suggests using them to detect gravitational waves, not by measuring space-time ripples directly, but by monitoring how those ripples subtly disrupt the clock's perfect cadence. Yet the most profound application might be historical. Unlike human timekeeping, which resets with each new civilization, these cosmic clocks have been ticking since the star's birth. By comparing current orbital periods with ancient astronomical records like Babylonian eclipse observations or Chinese star catalogs, we can measure how time itself has flowed over millennia. Preliminary studies suggest some systems show minuscule but consistent slowdowns, their orbits stretching by microseconds per century due to the universe's gradual energy loss. It's as if we've stumbled upon the universe's own hourglass, silently marking the passage of cosmic epochs. But the true marvel isn't just their accuracy, it's their resilience. Even as stars age, explode, or collapse, their gravitational choreography preserves timing information like a celestial blockchain. The white dwarf remnants in system WD0422 plus 099 still pulse along the same rhythm their progenitor stars established billions of years ago, their orbits now encoding not just time but the memory of the system's violent transformations. For astronomers, these systems are more than curiosities, they're living archives. Every synchronized orbit, every resonant pulse is a thread in the fabric of cosmic time, woven so tight that not even the universe's chaos can unravel it. And as we learn to read their rhythms, we're not just keeping time, we're deciphering the universe's deepest heartbeat. From gravitational dances that warp time itself to zombie stars that refuse to die, the 30 strangest discoveries in sextuple star systems have rewritten astronomy's rulebook. These cosmic oddities, stellar vampires, phantom black holes, and planets orbiting 6 suns aren't just quirks, they're gravity's boldest experiments. Take the hypervelocity runaways flung across the galaxy by sibling stars, or the magnetic maelstroms where entangled stars pulse in eerie sync. Each revelation peels back another layer of stellar behavior we once thought impossible. Consider the paradoxes: systems where stars shouldn't survive yet thrive for eons, or dead white dwarfs that cling to their families like celestial ghosts. These aren't just anomalies, they're cosmic masterclasses in chaos and order. The precision of eclipsing binaries gives us micrometer-accurate stellar measurements, while the rogue intruders that hijack orbits remind us these systems are never static. Even time bends to their will, with relativistic effects making clocks tick slower just by proximity, and the implications ripple far beyond astronomy. Quantum-like entanglement between stars challenges our understanding of physics at cosmic scales. The potential for habitable niches in these gravitational tornadoes forces us to redefine life-friendly zones. Every discovery in these systems is a testament to the universe's creativity, proof that the boundaries of what's possible are drawn in stardust, not stone. The greatest lesson: we've only scratched the surface. For every sextuple system we've mapped, countless more lurk in the dark, each holding secrets that could upend another fundamental assumption. So keep looking up. The next time you gaze at the night sky, remember, out there, 6 star families are performing ballets we've yet to imagine, and the universe is just waiting for us to tune in. The cosmos never runs out of surprises, it's just calibrating the next revelation.